Look up tonight, not at your phone, not at a screen. Look up, somewhere above the glow of cities and the hum of highways, beyond the thin blue skin of Earth's atmosphere. There are billions of stars inside our galaxy alone, and around many of those stars billions of planets. Statistically, mathematically, overwhelmingly, it feels impossible that we are alone. For decades, American culture has absorbed this assumption. Hollywood told us they're out there. Television normalized it. Headlines hint at it. The Pentagon releases blurry footage and the internet explodes. The belief settles into something comfortable: the universe must be crowded. But what if that comfort is a misunderstanding? What if the silence in the sky is not mysterious at all? What if it is the only outcome physics ever allowed? Tonight, we are not following hope. We are not following imagination. We are following the laws that actually govern reality, and those laws do not negotiate. If you value hard science over comforting stories, stay with me. Because when we apply a physics-first mindset, when we think the way Richard Feynman demanded we think, we may discover that the universe is not silent because nobody is there. It may be silent because nobody can ever reach anyone else, and that is far more unsettling. Before we go further, if you appreciate science grounded in evidence, consider subscribing. Like the video if you believe physics matters more than fantasy. And in the comments, tell me which part of the United States you're watching from. Coast to coast, from small towns to big cities. I'd love to see how far this conversation travels across the country. Richard Feynman, the Nobel Prize-winning physicist, was famous not just for brilliance but for intellectual honesty. He insisted on one uncompromising rule: follow the math, not the hope. If your idea conflicts with experiment, it is wrong. Not maybe wrong, not philosophically debatable wrong. That mindset is our guide here. Because the question, where is everybody? What physicist Enrico Fermi famously asked during a casual lunch conversation, only feels mysterious if we begin from emotion. It feels obvious that life should spread. It feels obvious that intelligence should expand. It feels obvious that a sufficiently advanced civilization should cross the stars. But nature does not run on feelings, it runs on constraints. The first constraint is scale. Human intuition evolved on a planet 8,000 miles across. We navigate cities, states, maybe continents. The largest distance most Americans routinely comprehend is the width of the country, about 800 miles coast to coast. Even the distance to the moon, roughly 238,000 miles, feels abstract but manageable because we have physically gone there. But the nearest star beyond the Sun, Proxima Centauri, sits about 4.24 light-years away. A light-year is not a measure of time, it is a measure of distance. It is how far light travels in 1 year, about 5.88 trillion miles. Multiply that by 4.24. You are now looking at a distance of roughly 25 trillion miles. That is the nearest possible neighboring star system. Not across the galaxy, not across the universe, the nearest. And our fastest spacecraft ever built, the Parker Solar Probe, moves at roughly 430,000 miles per hour at peak velocity. That sounds astonishing until you do the math. At that speed, reaching Proxima Centauri would take thousands of years, not decades, not centuries. Thousands. This is where Feynman's mindset becomes uncomfortable. We often respond, yes, but technology improves. Yes, but civilizations advance. Yes, but perhaps alien physics is different. That is hope speaking. Physics does not permit arbitrary acceleration. As an object approaches the speed of light, 186,282 miles per second, its energy requirement increases dramatically. According to Einstein's special relativity, accelerating a mass to light speed would require infinite energy. Infinite energy is not a technological hurdle. It is a physical impossibility. That speed limit is not a suggestion. It is built into the structure of space-time itself. So perhaps we travel at some fraction of light speed, say 10%. Even that is unimaginably difficult. The kinetic energy required to accelerate a spacecraft of modest mass to 10% of light speed is staggering. The energy scales with velocity squared. Double the speed, quadruple the energy. And you must not only accelerate, you must also decelerate upon arrival. That means carrying fuel, or finding fuel at the destination. Enter the rocket equation. The Tsiolkovsky rocket equation is brutally simple and devastatingly unforgiving. It describes how much fuel is required to achieve a desired change in velocity. The relationship is exponential. To gain more speed, you do not add fuel linearly. You add it exponentially. Want twice the velocity. You need far more than twice the fuel. And that fuel itself has mass, which requires more fuel to push it. This compounding requirement makes interstellar travel not just difficult, but almost absurd under known propulsion methods. Even nuclear thermal rockets, even fusion concepts, struggle under this tyranny. The math does not care how advanced you are. The math compounds against you. Some argue for exotic loopholes, warp drives, wormholes, space-time shortcuts. These ideas arise from real solutions in general relativity, but they require conditions never observed: negative energy densities, exotic matter with properties not known to exist in usable quantities. The equations permit strange geometries, yes, but permitting mathematically does not mean permitting physically. Feynman would ask, where is the evidence? Show me the experiment. Show me the energy source. Until then, speculation is not engineering. Now let us widen the view. The Milky Way galaxy is about 100,000 light-years across. If even one civilization arose 1,000,000 years before us, a blink in cosmic time, it might have had time to spread. But spreading requires crossing that immense scale under the constraints we just discussed. Even if a civilization launched self-replicating probes, machines that harvest local materials to build copies of themselves, the expansion speed would still be limited by sub-light velocities. At even 10% of light speed, crossing the galaxy would take 1,000,000 years. That sounds short in cosmic terms, but it assumes uninterrupted expansion, perfect reliability, no catastrophic failures, no resource bottlenecks, no internal collapse. It assumes stability across geological timescales. And stability is not guaranteed. Civilizations are fragile. Human technological civilization is barely a few hundred years old. Nuclear weapons have existed for less than a century. We already possess the capacity for self-annihilation. Add to this climate instability, biological risks, artificial intelligence uncertainties. The window during which a civilization can project power beyond its home world may be narrow. Physics allows only limited energy extraction from planets. Biology constrains lifespans. Sociopolitical systems fluctuate. Expansion may not be the default outcome. Extinction might be statistically more common. But even if a civilization survives, the biological problem remains. Space is not empty serenity. It is radiation. Cosmic rays, high-energy particles accelerated by supernovae and other violent events, slam into matter at near light speed. Without thick shielding, prolonged exposure damages DNA, increases cancer risk, disrupts cellular repair mechanisms. Microgravity weakens bones and muscles. Astronauts aboard the International Space Station lose bone density at measurable rates despite rigorous exercise. Now imagine decades or centuries in transit. Generation ships introduce another layer. Closed ecological systems must remain stable indefinitely. Tiny imbalances compound. Microbial evolution continues. Human psychology must endure confinement beyond any prison ever designed. Feynman loved to strip problems to essentials. What are the known quantities, energy requirements, biological fragility, radiation exposure, closed system entropy? Every one of these is grounded in experiment. None rely on speculation. When we stack them together, interstellar travel begins to resemble not a grand adventure, but a convergence of extreme improbabilities. And then there is time itself. Signals cannot travel faster than light. If a civilization 100 light-years away transmits a message, we will not receive it for a century. Our reply takes another century, 200 years for a single exchange. Communication across galactic scales becomes effectively asynchronous archaeology. By the time you hear from someone, they may be gone. By the time they hear from you, you may be extinct. The universe does not allow real-time cosmic conversation. Now consider detection. We search for radio signals, technosignatures. But radio leakage from Earth is weakening as we move to fiber optics and directional transmissions. Our loudest broadcasts may only persist for a brief technological phase. If other civilizations follow similar trajectories, the detectable window could be short. Two civilizations must overlap not only in space but in technological time. The odds shrink further, and here is where the silence begins to feel less mysterious. It is not that life cannot arise. It may arise often. But physics erects barriers between islands of intelligence so vast that contact becomes statistically negligible. Imagine the United States without airplanes, without radio, without satellites, just isolated towns separated by impassable mountains thousands of miles wide. Now multiply that scale by trillions. Modern UFO videos often circulate as evidence of visitation. But apply Feynman's test. Does the motion obey known aerodynamics? Does the sensor data rule out mundane explanations? Is the resolution sufficient for quantitative analysis? Blurry infrared clips with ambiguous depth cues fail basic physical scrutiny. Extraordinary claims require extraordinary evidence, not emotionally compelling footage, but repeatable measurement. Advanced civilizations capable of crossing interstellar distances would command energies rivaling stars. Their arrival would not resemble a smudge on a Navy camera. It would involve detectable astrophysical signatures, propulsion exhaust, energy emissions orders of magnitude beyond conventional aircraft. We do not see that. The silence, then, is not evidence of Ab's constraint. The speed of light enforces isolation. The rocket equation punishes ambition. Radiation erodes biology. Time dilutes communication. Entropy destabilizes closed systems. These are not temporary engineering bugs. They are structural features of reality. And yet this conclusion does not diminish humanity. It elevates it. If civilizations are separated not by hostility but by physics, then Earth is not one insignificant speck in a crowded cosmic city. It may be one of countless lonely lights, each unable to bridge the abyss. Rarity does not require uniqueness. Even if life is common, interaction may be rare beyond comprehension. Feynman once said that reality must take precedence over public relations because nature cannot be fooled. We might want a universe teeming with visitors. We might want confirmation that we are part of a grand galactic community. But wanting does not bend equations. The universe operates on principles discovered through experiment, measurement, and mathematical consistency. Those principles are mercilessly impartial. As we continue, we will examine 5 absolute verdicts imposed by physics, limits so severe that no intelligence can repeal them. We will explore energy ceilings, propulsion barriers, biological decay, detection limits, and cosmic timescales, not to depress, not to sensationalize, but to understand. Because when you truly accept these constraints, something shifts. The silence stops being eerie. It becomes expected. The night sky stops feeling like a crowded auditorium waiting to applaud us. It feels like a vast wilderness where each campfire burns unseen by the others. And in that realization, Earth becomes profoundly precious, not because we are chosen, not because we are alone, but because physics may have made us unreachable. This is not pessimism, it is perspective. And perspective, grounded in evidence, is far more powerful than fantasy. That belief is deeply American. It is woven into frontier mythology, into the Apollo era, into Silicon Valley optimism. We solved flight. We split the atom. We walked on the moon. So surely, given centuries or millennia, we will cross the stars. Surely somewhere out there, someone already has. But Feynman's discipline does not ask what we have historically overcome. It asks what the equations forbid. And the more carefully we follow those equations, the clearer it becomes. The silence of the universe is not a temporary condition waiting for better engineering. It is the stable outcome of 5 physical verdicts that no civilization escapes. The first verdict is distance, but not distance in the poetic sense. Distance is measured by energy per unit mass. To move something through space requires energy. To move it very fast requires extraordinary energy. The kinetic energy of an object increases with the square of velocity. That relationship is not political. It is not cultural. It is not technological. It is embedded in the structure of motion itself. As velocity approaches the speed of light, relativistic effects amplify the cost further. Mass effectively increases relative to an external observer. Time dilates, length contracts. But from the perspective of propulsion, what matters is this: the closer you get to light speed, the more violently the universe resists additional acceleration. Infinite energy would be required to reach light speed. Not a lot of energy. Infinite, that word closes doors. Perhaps then civilizations settle for slower travel. 10% of light speed. 1%, about 1.86 million meters per second. The energy required to accelerate a modest 100-ton spacecraft to 1% of light speed is on the order of 4.5 × 10^17 joules. That is roughly the total energy consumption of the entire United States for many days, poured into a single launch. And remember, you must decelerate when you arrive. Double the energy. And unless you invent reactionless propulsion, which violates conservation of momentum, you must carry propellant. That propellant mass feeds back into the rocket equation exponentially. The tyranny compounds. This brings us to the second verdict: propulsion is not limited by imagination, it is limited by conservation laws. Momentum must be conserved. Energy must be conserved. These are not suggestions, they are symmetries of nature formalized through Noether's theorem. Every propulsion system, chemical rockets, ion drives, nuclear thermal engines, fusion concepts, must push against something. If you throw mass backward, you go forward. If you emit photons, you recoil slightly. There is no free thrust. Even hypothetical antimatter drives face staggering constraints. Producing antimatter requires at least as much energy as you hope to extract from it, usually far more due to inefficiencies. Containing it safely at scale is another problem entirely, and if you try to push against magnetic fields or quantum vacuum fluctuations without ejecting reaction mass, you quickly encounter violations of well-tested physical laws. The universe guards its conservation rules jealously. The third verdict is radiation. Interstellar space is not empty. It is filled with high-energy particles traveling near light speed. At velocities approaching even a few percent of light speed, collisions with microscopic dust grains become catastrophic. A grain of sand impacting a spacecraft at 10% of light speed releases energy comparable to explosive detonation. Shielding against such impacts requires mass. Mass requires more propulsion energy. Again, meanwhile, galactic cosmic rays penetrate, shielding, damaging electronics and biological tissue. DNA breaks accumulate. Cancer risk increases. Neural degradation becomes possible. Magnetic shielding concepts exist, but they require large-scale electromagnetic fields and immense power generation. Biology evolved under Earth's magnetic field and atmospheric protection. Strip that away for decades and the fragility becomes evident. The fourth verdict is time. Civilizations are not static. They rise and fall. Stars themselves evolve. The average lifetime of a technological civilization is unknown, but even optimistic estimates must contend with internal risk. Climate instability, resource depletion, warfare, artificial intelligence misalignment, pandemics, these are not science fiction. They are observable vulnerabilities. For two civilizations to meet, they must overlap in time while also overcoming spatial separation. Imagine two fireflies flashing once per century in a forest the size of a continent. The probability of synchronized visibility becomes vanishingly small. But even if civilizations persist for millions of years, communication remains throttled by light speed. A galaxy 100,000 light-years across imposes a minimum 100,000-year one-way signal delay from one side to the other. No centralized network can function across that scale. No political unity can meaningfully coordinate. The Milky Way is not a city. It is an archipelago separated by abyssal oceans measured in millennia. The fifth verdict is thermodynamics. Entropy increases. Closed systems degrade. Life requires energy flow to maintain order. A spacecraft or sealed habitat is a temporary defiance of entropy powered by stored energy or continuous input. Over long durations, maintaining perfect recycling becomes nearly impossible. Even tiny inefficiencies accumulate. Materials fatigue. Microfractures propagate. Chemical imbalances creep in. Evolution does not pause in closed systems. Microbes adapt. A generational ship must remain stable across centuries without resupply. That is not merely an engineering challenge. It is a statistical battle against compounding uncertainty. Now step back and combine these verdicts. Distance demands extreme energy. Energy demands mass. Mass increases propulsion cost. Propulsion amplifies radiation exposure. Radiation degrades biology and electronics. Time dilutes synchronization between civilizations. Entropy destabilizes long-term systems. Each factor alone is daunting. Together they form a lattice of constraint. And yet, popular culture often imagines advanced civilizations sidestepping these limits effortlessly. Faster than light travel becomes routine. Galaxies become neighborhoods. But every proposal for faster than light travel runs into causality problems. If information can travel faster than light, cause and effect can reverse order in certain reference frames. Paradoxes emerge. Special relativity tightly binds the speed of light to the structure of spacetime. General relativity allows mathematical solutions like wormholes, but they require negative energy densities not known to exist in usable macroscopic quantities. Even if quantum effects permit tiny negative energy fluctuations, scaling them to spacecraft size appears incompatible with known quantum field theory. Again, Feynman's rules show me the experiment. Let us apply this reasoning to modern UFO claims. Videos often depict objects accelerating rapidly without visible propulsion. But apparent acceleration in a 2D sensor frame can result from parallax, camera rotation, or misinterpreted distance. Without precise range data, velocity estimates collapse. Extraordinary maneuvers require enormous energy changes. Rapid right-angle turns at hypersonic speeds would impose extreme g-forces. Biological occupants would be liquefied unless inertial dampening. Another speculative concept without empirical basis exists. If propulsion involved manipulating spacetime itself, the energy signatures would dwarf conventional aircraft emissions. We would detect gravitational anomalies, radiation bursts, or other measurable disturbances. We do not. Blurry imagery is not evidence, it is absence of resolution. If truly advanced civilizations exist, perhaps they choose not to reveal themselves. But concealment itself has physical costs. High-energy propulsion cannot be hidden easily. Stellar-scale engineering, Dyson spheres or swarms, would alter star spectra measurably. Astronomers search for such anomalies. Thus far, natural explanations suffice. The cosmos appears astrophysically ordinary. This is where the Fermi Paradox dissolves. It was never truly a paradox. It was a tension between intuition and scale. Intuition expects expansion. Physics enforces isolation. The silence is not eerie once you internalize the constraints. It becomes statistically plausible, even likely. But here is the deeper shift. If interstellar contact is physically suppressed, then each biosphere becomes a self-contained experiment in complexity. Earth's evolutionary history spans 4.5 billion years. For most of that time, life was microbial. Complex multicellular organisms are recent. Technological civilization is a flicker within that. If intelligence is rare and interstellar bridges are nearly impossible, then Earth's biosphere is not just one node in a bustling network. It may be one of countless isolated miracles, each burning alone. This perspective reframes significance. The common narrative says the universe is vast, therefore we are insignificant. But physics suggests something subtler. Vastness plus constraint implies rarity of interaction. Rarity implies preciousness. If no rescue is coming, stewardship becomes mandatory. If no galactic federation exists, responsibility remains local. Feynman emphasized intellectual humility. The first principle is that you must not fool yourself, and you are the easiest person to fool. It is easy to fool ourselves into believing that advanced technology cancels physics. It does not. Technology rearranges matter and energy within the boundaries physics permits. It does not rewrite those boundaries. Could future breakthroughs change our understanding? Of course. Science evolves. But revolutions in physics do not usually erase conservation laws, they deepen them. Quantum mechanics did not abolish energy conservation. Relativity did not abolish momentum conservation. They reinforced them in more generalized forms. Any future framework must recover the current one as an approximation where it has been tested. And current tests of relativity and quantum field theory are extraordinarily precise. So what remains? Exploration within limits. Robotic probes to nearby stars traveling over millennia. Communication attempts knowing replies may outlast civilizations. Astronomical observation is our primary window into cosmic life. Perhaps biosignatures in exoplanet atmospheres, oxygen disequilibrium, methane combinations will reveal life's presence without physical meeting. We may confirm we are not alone biologically, while remaining permanently isolated technologically. That is not a tragedy. It is a reality shaped by constants, the speed of light, Planck's constant, the gravitational constant. These numbers govern every star, every galaxy. They do not bend for desire. And so the silence of the universe is not a taunt. It is a consequence, a natural outcome of energy scaling, relativistic limits, thermodynamic drift, and temporal mismatch. Once you accept this, the night sky changes character. It stops feeling like a stage waiting for visitors. It feels like a cathedral of distant fires, each separated by gulfs no ship can practically cross. There may be civilizations out there. Some may look up at their own skies and wonder the same thing. They may run the same calculations. They may reach the same conclusion. They may cherish their own fragile worlds precisely because the cosmos is unreachable. And here on this small planet orbiting an ordinary star in an ordinary galaxy, we are not insignificant spectators. We are participants in a rare and delicate phenomenon, matter that has learned to question the universe. The silence does not diminish that, it amplifies it. Because if physics prevents civilizations from meeting, then the only minds that will ever know Earth are the ones already here. And that makes this planet not the center of the universe, but something arguably more extraordinary. It makes it irreplaceable.